Now we come to another important topic in the subject of theory of machine, from which many gate questions are asked every year. This is a topic of mechanical advantage. The mechanical advantage is used in a machine to calculate the transmission ratio. It is also called gain in some terminology in electronics, particularly in the machine from input to output. So a machine, as we saw earlier, is nothing but a mechanism with transformation and transmission of forces or torque in the angular terminology. So machine is used for this purpose. So in a mechanism, you have an input which is also called a driver, which drives the mechanism, and you have a load which is output of the mechanism, the output force, output torque, and it is also called the driven link. Okay, so the ratio of load to effort. Effort means how much energy you are giving into the system. The input or driver is also known as effort. So input to the energy to the load to the output. The ratio of forces at this location or torque at these two locations is known as mechanical advantage that we are going to cover here. This is an important topic because at least one or two questions you will find in GATE from this topic where a mechanism will be given and you have to calculate the mechanical advantage. We will consider the mechanical advantage for a 4-bar chain here. The ratio of load to effort. The important thing to remember here is that load is in numerator and effort is in denominator. For 4-bar chain, we will look at this. This is a fixed link. This is the input link, which is rotating at angular velocity of omega A. This is the output link, which is rotating at angular velocity of omega B. We will name the joints as A, B, C, and D. So AD is the input or effort or driver link, and BC is the output or load link or driven link. So we are interested in transmission of forces. So let's say a force FA is applied at the joint A. The velocity of point A will be in a direction perpendicular to the link AD, the velocity being VA. Similarly, for link B, the force applied will be FB and the velocity will be perpendicular direction to the link BC, and we will term it the velocity as VB. Now, since we are interested in the input effort to the output effort, this being a rotational system, since things are moving in with angular velocity, we will consider torque. So the torque for input TA will be equal to cross product of the force and the link AD. So the cross product will ensure that the component normal to the link AD is taken into account. So FA cross AD. Similarly, the output torque or the resisting torque will be equal to TB is equal to FB cross BC. The output torque is also called resisting torque because there will be a load connected to the output, and the load will have a reaction. So FB is basically the reaction force. FB amount of force will be transmitted to the load, and same amount of reaction force will come to the mechanism. So that's why it's called a resisting torque also. Now the input link is moving at an angular velocity of omega a, and the output link is moving at an angular velocity of omega p. So the power in angular motion, as you are aware, is equal to torque multiplied by angular velocity. In linear system, the power is equal to force into velocity. Similarly, in angular system, we have torque into omega. So the input power to the system is input torque, that is TA, multiplied by input angular velocity, that is omega a. Similarly, the output power from the system is the output torque TB multiplied by output angular velocity. This is also called the resisting torque TB. So, from the principle of conservation of energy, we will get the equation for mechanical advantage. So, the power is nothing but energy per unit time. So, since the input energy is equal to output energy, that's why input energy per unit time is equal to output energy per unit time. Hence, input power is equal to output power, and hence TA omega A is equal to TB omega B, considering that there are no losses in the mechanism. So from the relation that TA omega A is equal to TB omega B, we get TB by TA is equal to omega A by omega B. Now the mechanical advantage was defined as load by effort. So in the present case, this means output torque divided by input torque. So this quantity is equal to TA B by TA. B is output. That becomes omega A by omega B. So it is interesting to note here that in a 4-bar chain or in any mechanism in general, it is very easy to determine the ratio of angular speeds of different links by kinematic analysis. By doing displacement analysis, you can get the ratio of angular velocity. So, based on our earlier velocity analysis, so that we will be covering shortly in coming lectures, you can get the ratio, and then from that you can get the mechanical advantage by taking ratio of the angular velocity. This quantity omega A by omega B is known as ideal mechanical advantage. That means there is no loss in the mechanism. But in actual case, there will be a loss due to friction in a real mechanism. So that time, the real mechanical advantage is calculated by multiplying an efficiency factor with the ideal mechanical advantage. So this efficiency factor is called the conversion efficiency, So it is a percentage of 100, which is a value less than 1. So you multiply the ideal mechanical advantage with the conversion efficiency eta, and you can get the real mechanical advantage. So if you substitute the value of ideal mechanical advantage, you get eta multiplied by omega A by omega B. The angular velocity of the input link divided by angular velocity of the output link. So for the torque, it was TB by TA. The torque at output divided by torque at input. For the omega, it becomes reverse. So we'll consider some questions based on the concept of mechanical advantage. There are because at least 1 or 2 questions you'll get in GATE from this topic. This is a 4-bar chain that is given in the problem. This is a fixed link, and we have A, B, C, D as we shown earlier. So this is the driven link. So the driver link, and this is the driven link. The speed of this link is omega A, the speed of this link is omega B. The problem given is that driver rotates uniformly at 120 rpm and is having constant driving torque of 15 Newton meter at a particular phase of the mechanism. That means at an instantaneous position at some point in time. You can consider the mechanism position to be frozen at that time. So the particular phase or time instant, the angular velocity of driven link is 2 radians per second. The question asked is calculate the mechanical advantage. And the second part, this is the first part of the question. Second part of the question, what is resisting torque if efficiency or conversion ratio of chain is 70%. So the angular velocity of the driver here is 120 rpm. So in radian per second, it will come as 2 pi into rpm divided by 60. That is equal to 12.56 radian per second. So we know the input angular velocity, we know the output angular velocity. So by substituting in the equation of the mechanical advantage, the ideal mechanical advantage, which is equal to omega A by omega B, input angular velocity by output angular velocity, that is 12.56 divided by 2, this comes now 6.28. So this is the value of ideal mechanical advantage. So this is the answer of part 1, that calculates the mechanical advantage. Now you should have noticed here that for calculating the mechanical advantage, we didn't need the information about the torque which is provided here. This will be used in the second part of the problem to calculate the resisting torque, but for calculating the mechanical advantage, you don't need the amount of torque. Now for the second part of the problem, which is asking about resisting torque if the efficiency is 70%. It has to be 70%. So the input torque is given. The value of input torque is 50 Newton meter. So we know the value of ideal mechanical efficiency from the part 1 of the problem, that was equal to 6.28. So the real mechanical advantage will be equal to efficiency of the system into ideal mechanical advantage, that is equal to 0.7. 70% means 0.7. 70% divided by 100 multiplied by 6.28. So this comes 4.396. Okay. So the mechanical advantage, real mechanical advantage, is equal to output torque divided by input torque. For ideal mechanical advantage, like real mechanical advantage is taking into account the efficiency, while the ideal is not taking into account efficiency. So here we want real output torque, so we are taking real mechanical advantage. So here if you substitute the values, you get the real mechanical advantage. You substitute the value of 4.396. The output torque is unknown, and the input torque is 50 Newton meter. So the output or resisting torque is equal to 4.396 multiplied by 50, around 1220 Newton meters. So this is the answer for the part 2. The important point to note in this question is that when output torque is asked, you should always consider real mechanical efficiency, mechanical advantage, because in a real system there will be frictional losses, and if it is the efficiency of the mechanical system is not given, then you can assume ideal mechanical advantage as the real advantage if friction is zero. But you should always opt for real mechanical advantage. Now we move on to a very important topic, that is the dynamic analysis of slider crank mechanism. So from here we start our second module in the chapter 1 of theory of machine. Till now we described the mechanism, how they are formed, and we did kinematic analysis. Now we will move forward to the dynamic analysis, and this we will start with the example of slider crank mechanism. Later on there will be a little bit on the 4-bar mechanism. So till now we saw how a mechanism is formed by ratio of various linkages, lengths, and Grashoff's criterion, what kind of movements are possible in the mechanism. Now we will take up the specific example of the slider crank mechanism, and we will understand how velocities are coming. We will analyze velocities, acceleration, and forces due to acceleration. So that's why, since the forces and velocities have came into picture now, so now we are doing dynamic analysis. Till now we were doing kinematic analysis, how the mechanism motion is allowed, how the relative displacements would be. So now we will start the dynamic analysis. For that, I'll draw our standard 4-bar chain mechanism, and we will put some basic terminology in place. This is our standard 4-bar chain. Here the crank is pivoted, crank is rotating. This is link OA. This is our piston. This is connecting rod, and the connecting rod is AB, and AB is having a sliding pair with the liner. So here the sliding takes place. The length of the connecting rod is L. The length of the crank is R. This is the pin joint between connecting rod and crank. And if you draw trajectory of the joint A at the end of the crank, it will form a circle. We will draw an approximate circle here. I will draw the coordinate system and axis here. I will drop a projection here that will help us in the calculation. So this is the trajectory of the joint A of the crank. The point when the joint is farthest from the piston assembly, this point is known as outer dead center. And the point when it is closest to the piston assembly, this is known as inner dead center, IDC. The uniform angular velocity of the crank is omega. Let's say the connecting rod will make the angle beta with respect to the horizontal axis, and the crank is making angle theta at a particular time instance. When the crank is at inner dead center, the piston will also be at its farthest position from the center of the crank. So this is known as IDC, inner dead center of piston. So for that time instance, the crank will be lying in the horizontal position and the piston will be farthest. And at 180 out of phase, the piston will be at the point closest to the crank center. This is known as outer dead center of the piston. So we are interested basically in the displacement of the piston at any particular time instance from the inner dead center, that is x. So x is displacement of piston from inner dead center at a time instant t. So the known parameter in the problem is L, length of connecting rod, R, length of crank, and the instantaneous properties that will change with time are x, displacement of piston, beta, angle of connecting rod with respect to horizontal, and theta, angle of crank with respect to horizontal. These are the geometrical parameters. The velocity parameters provided is omega, that is angular speed of crank. So our task is that with the help of a known parameter, that is L, R and omega, and at particular instance the theta, the angle of the crankshaft, we have to determine the x and beta and the velocity of the piston. So the main problem here is that to determine velocity and acceleration of piston. This is the problem, and in GATE examination also you will find questions where L, R, theta, these quantities are given and you have to determine velocity and acceleration of the piston. So this we will do with the help of trigonometry of this system.